Hello, this is Jack Jackson. In this video, we're going to look at how vertical shifts affect derivatives, or rather, how they don't affect derivatives. This GeoGebra app that I've written, you can type in a formula for a function. Here I'm just using our good old familiar f of x equals x squared. And then to that, we can add c to that function to get a new function. And you notice that that's just a vertical shift of the original function. If c is 0, it's the same function. If c is positive, we're shifting the function up. If c is negative, we're shifting it down. So let's just say we go to, I can type in a number here, or use the slider to do it. So let's say we let that be 4. Here I can pick an a value, which is an x value. And above that a value of a, we have the 2 points here on the graph. Notice that we can change the value of a by changing this point a on the x-axis down here. We can change it by the slider up here, or we can type in a point like 1, for example. Now the question is, what happens to the derivative? Well, remember, the derivative is the slope of the tangent line, so I have the tangent line drawn in here at this point. Well, since the function is just a vertical shift of the other function, the tangent line is also just a vertical shift. If you take a particular x value, the shape of the graph is the same for a certain x value. The slope is the same particularly. So these tangent lines are parallel. They have the same slope. So the derivatives are the same. Okay? In this case, the derivative function is graphed right there, and it's the same derivative function regardless of what we put for the c value of c. Proof is super easy. The derivative of f of x plus c of x by the sum rule is the derivative of f plus the derivative of c. By the constant function rule, the derivative of c is 0. 0 plus f prime of x is just f prime of x. So this is the derivative of f of x, g of x, which is f of x plus c. It's still the same thing as the derivative of f. And so we can see that. Now, one of the things that is important about this is particularly important when we start thinking of reversing the process of finding a derivative. In other words, the process of finding an antiderivative. The process of finding a derivative is itself a function. If we take one, it takes a function as the input and it outputs a derivative function, a one and only derivative function. So whether we're taking this function here, f of x, or this function here, f of x plus c, the output is a single derivative function, this line here. Okay? If you try to go backwards, however, and do an antiderivative, we started with this function and we find a function whose derivative is this one. There's not just one. There's this f, it could be x squared, but it could be x squared plus, also x squared plus any constant. All of these have the same derivative. So all of these functions, all of these green ones, no matter what I pick for c, including c is 0 and get the red one, or the blue one, they give you a derivative, which is this red graph. In this case, it's y equals 2x. And so what we see is this process of finding an antiderivative is not a function. So the process of differentiation is itself a function. It takes an input function and its output is a single function. But going backwards is not a function because the differentiation is not one-to-one. It gives you infinitely many functions that have the same derivative. So what this tells us, when we get to later on, we're going to reverse the process of finding derivatives to find antiderivatives. We're not going to find a single antiderivative. We're going to find an entire family of antiderivatives, all of which are really just the same function plus different values of c. So when we do antiderivatives, we're always going to have a plus c to get an entire family of antiderivatives. Okay, see you later for the next one.